All right, so in this presentation, we're going to be going over group designs. This presentation goes over the following two group designs. We have randomized controlled trials, or RCTs. These are also called true experiments because we have randomized participants to groups. And we have quasi-experiments, and the difference between them essentially is that a quasi-experiment doesn't involve randomization on the individual level to groups. So RCTs randomized at the individual level, quasi-experiments are randomized or are not randomized. We start with the foundations of why we are looking at the designs that we are looking at and why I am spending so much time on these particular designs. The Every Student Succeeds Act of 2015 defined an evidence-based practice, and they defined when we need those evidence-based practices. And we need those evidence-based practices when we're working at title schools or working with schools that have been found to be low performing, and I think it's called targeted intervention or something like that. So we have two areas where we have to use evidence-based practices according to the law, and that again is title schools and schools that are considered non-performing. And an evidence-based practice is one that demonstrates a statistically significant effect on improving student outcomes or other relevant outcomes based on strong evidence from at least one well-designed and well-implemented experimental study. And by an experimental study, they mean a randomized control trial. Moderate evidence from at least one well-designed and well-implemented quasi-experimental study, or promising evidence from at least one well-designed and well-implemented correlational study with statistical controls for selection bias. Then we move on to the What Works Clearinghouse, and the What Works Clearinghouse was developed based on the passage of the No Child Left Behind Act, which the Every Student Succeeds Act is the reauthorization of. And they list four designs so the What Works Clearinghouse was developed by the Institute for Education Sciences, and it is a repository for reviews of literature, essentially, that look at determining what is an evidence-based practice or the extent of an evidence of an intervention on a specific outcome. So if I go up to the What Works Clearinghouse on Google, what we will find is that if we look at literacy, we can look for, we can look at the evidence for different reading programs and whether or not those are determined to be evidence-based or not. And so I know one of the ones that's used a lot around here is Read 180. And so it will give us a evidence snapshot. It'll give us an intervention report. This was found to have positive effects on comprehension and general literacy achievement, potentially positive effects on reading fluency, and no discernible effects on alphabetics or adolescent readers. So 9 studies met the standards out of 39 eligible studies reviewed. And you can see the effectiveness rating, the improvement index, and you can see other things. And then we have an intervention report that would also go along with it. So the WWC, the What Works Clearinghouse, is the repository for IES to determine whether or not a practice is evidence-based or not. So they list these four designs as eligible for determining those things. So if it's not one of these four designs, the What Works Clearinghouse will kick the study because it doesn't meet the design specifications that they have determined are effective designs. So we have randomized controlled trials, quasi-experiments, but these quasi-experiments have to be quasi-experiments that have a control group. So they might not be randomly assigned to the control group, but there is a control group. We have regression discontinuity designs, which we'll talk about later, and we have single case designs. So today we're going over RCTs and quasi-experiments. So randomized controlled trials. An RCT is a planned experiment designed to assess the efficacy of an intervention in human beings by comparing the intervention to a control condition. The allocation to intervention or control is determined purely by chance or randomization, and RCTs are a subset of possible experimental designs. Randomization avoids selection bias, improves comparability of the intervention and control arm populations. E.g., for example, we can match or block units of randomization, and fulfills the assumptions underlying tests for statistical inference. So if it's random, we would expect that we would not violate the assumption of normality and those types of things. What does controlled imply? Control implies eligibility criteria is predefined, specified hypotheses, primary and secondary endpoints, for example, behavioral change, HIV incidence, reading fluency, etc. Methods for enrollment and follow-up, rigorous monitoring and analysis plans, and stopping rules. So why do we do these? Observational and quasi-experimental designs are subject to potential bias and confounding due to self-selection, which means a lack of comparability. We may have observer bias, and we may have secular trends, either before and after the study. The RCT provides the gold standard for proof of concept. Are they always valid? RCTs can provide conflicting results. In RCT design, the execution or the analyses can be flawed. Intervention versus control comparisons are internally valid, but restrictions on participant eligibility can reduce external validity. For example, specific age or sex groups may be omitted. So we have two types really of randomized control trials. We have individually randomized trials where eligible individuals are randomized, and self-selection of persons volunteering for enrollment are reduced. And then we have cluster randomized trials where communities, hospitals, schools, etc. are randomized and all consenting persons enrolled. And this involves less individual self-selection. So this cluster randomized trials are what we see a lot in educational research because we will randomize at the teacher level or at the class level rather than at the student level. And so if we are running a really big design, we can randomize schools, we can randomize classes, we can do those types of things so that we're still getting the randomization process, but we're not able to maybe randomize at the individual level. Why would we do a cluster randomized trial? If the nature of the intervention, population necessitate it, it has improved acceptability and reduces stigma because everyone gets the same treatment within a cluster. So the classes aren't saying, why is Johnny getting out of class, and etc. It can reduce participant self-selection and maximize generalizability. Can get data on many nested population subgroups and allows assessment of population level effects. But the limitations are that cluster randomization is more vulnerable to a lack of comparability between study arms and individual randomization because there's fewer of them. There may be fewer schools than you have actual students, so you might have 300 students but only at 2 schools or in or 4 classes or something like that. They increase the sample size requirements and are less efficient than individual randomized trials due to intercluster correlation. So the unit of randomization versus the unit of analysis. A key property of cluster randomization trials is that inferences are frequently intended to apply at the individual level, while randomization is at the cluster or group level. Thus, the unit of randomization may be different from the unit of analysis. In this case, the lack of independence among individuals in the same cluster, for example, intra-cluster correlation, creates specific methodological challenges in both design and analysis. So we look at this, and I love this slide, or I love this graphic anyways. I want to make it bigger so we can see it better. We have 2 types of error when we're looking at statistical tests and in the designs. Type 1 error is a false positive where this guy would tell this guy he's pregnant even though there's no way that he's actually pregnant. And a type 2 error, this person says they're not pregnant when in fact they are pregnant. In my opinion, it's better to make this error and say it's not happening even though it is, rather than say, oh, you're pregnant when there's no way that that's true. The key point, if the unit of inference is at the cluster level, then an analysis at the cluster level is appropriate and no consideration need be given to the intracluster correlation coefficient. From the perspective of sample size estimation and analysis, the challenges are no different from those that arise in individually randomized trials. So within the research world, we have a classification of phases of not necessarily design, but of what your research relates to. And the FDA and the World Health Organization classify individually randomized trials during the course of drug or drug evidence testing. Phase 1 is a small sample size, less than 100. This is to determine safety and preliminary evidence of effect. Phase 2 are larger trials, 100 to 200 people. They assess the safety, acceptability, tolerance, and probable effective dose. Phase 3 trials are 500 plus. They assess the efficacy of the intervention, the acceptability, side effects, and complications. And Phase 4 is post-marketing trials in the general population. Then we have the IES, the Institute for Education Sciences, which delivers grants to nonprofits and institutes of higher education to look at their grants to I don't know why I can't say this right now. Grants, federally funded grants for education research. And they have 4 goals. We have exploration, development and innovation, efficacy and replication, and effectiveness. In exploration, projects under exploration must analyze primary data, secondary data, or both, and will result in a conceptual framework that identifies the following: a relationship between a malleable factor and a student educational outcome, or factors that mediate or moderate this relationship, or both a relationship between a malleable factor and a student education outcome and the factors that mediate or moderate this relationship. So, this includes primary data collection and analyses, secondary data analyses, meta-analyses, etc. In the development and innovation, so I have written 2 of these that are in review right now. The goal supports the development of new interventions and the further development of existing interventions that are intended to produce beneficial impacts on student education outcomes when implemented in authentic education settings. And in these, they expect that it's pretty much already developed and that you're just tweaking things. And then they would expect that you are doing a low-powered or medium-powered study at the end of it, so with 100 or 200 or so students. And that design would have to be one of those designs listed in the WhatWorks Clearinghouse. So it would have to be a randomized control trial, a quasi-experiment, regression discontinuity, or a single case design. In Goal 3, the efficacy replication goal supports the evaluation of fully developed education interventions to determine whether they produce a beneficial impact on student education outcomes relative to a counterfactual. So generally speaking, we would do the development and innovation grant first. We would have results from a study that showed this to be effective, and then we would apply for a Goal 3. And then in Goal 4, we have an effectiveness grant, supports the independent evaluation of fully developed education interventions with prior evidence of efficacy to determine whether they produce a beneficial impact on student education outcomes relative to a counterfactual when they are implemented by the end user under routine conditions in authentic education settings. Unlike efficacy and replication, effectiveness projects evaluate only interventions with prior evidence of efficacy when implemented without special support. So in this one, we would do a randomized control trial that would be fairly robust with good power, and then we would go here, and then this one would be essentially the same thing, but we would be expecting that teachers and school personnel would be the ones involved in implementing it. So now we go on to designs. Most trials have 2 arms. We have an intervention versus a control. I'm looking at doing a study in the spring that looks at 3 arms. So there would be an intervention versus, or there would be 2 different interventions and a control condition. Multiple interventions can also be compared to a single control arm. Equivalency trials, head-to-head comparison of 2 or more treatments without a control group, for example, contraceptive trials. Factorial designs, for example, intervention A, intervention B, intervention A plus B versus control. When should we do a trial? Trials must have a rationale based on prior observational data or biologic evidence, an explicit, testable, and potentially falsifiable hypothesis, an uncertainty as to whether an intervention is effective, reasonable expectation that benefits will exceed risk, and an intervention that potentially can be randomized. We went over ethics, hopefully, when you did your IRB training. So we should have a fairly good understanding of the Stanford prison experiment or those types of things. If we know something is an effective treatment, we cannot use a placebo. We need to provide against the standard of care. In this case, in educational research, we're usually going against a business as usual condition, which would be whatever is happening within the classroom, but we would still need to, so they're not getting nothing, they're getting whatever happens in the classroom, but we would also need to figure out a way to operationalize what's happening in the classroom. So this becomes a little bit difficult when we're working with counseling and those kinds of things, where somebody would say, well, I just want to counsel for 6 weeks and have that be my intervention. And if it's not a manualized program, it's hard to, you basically have to make lesson plans and have it manualized in some way so that when we write our procedures and we're doing those kinds of things, we know exactly what you're going to be doing when you're in there. Because if we just leave it up to you, we don't know what was happening in there, and it could have been good, it could have been bad, etc. Personal choice. We cannot randomize very different interventions. For example, trials of different types of contraceptive are ethically questionable because women have the right to select a method of their choice. Risks of new treatment likely to exceed risks of existing treatment. That may or may not be the case. With respect to sample size, the What Works Clearinghouse wants 350 participants for a randomized control trial with no reservations. We can do power analyses, which would essentially tell us that at P05 and at 0.8 power, we put those things in there. How many participants would we need? We need 128 participants, 64 per group, to arrive at an effect size, D, of 0.05. That should actually be lowercase. That should be lowercase. Why can't it be lowercase? Oh, because of the fonts. Yeah. Let's go ahead and give that a different font because I want that to be lowercase. D. That's still not going to do it. That's weird. All right. Anyways. Notes about power. The size of effect expected inside the sample may vary. So if we expected a medium effect of between 0.3 and 0.8, that'll bring our need for sample size down. If we have a bigger sample, we're able to see effects at a larger thing. And one thing that I want to reiterate is that P denotes significance. So this is our ability to determine whether or not it was significant or not. And then D is the most common effect size measure, and this denotes the magnitude, it's hard to write with a mouse, of the effect. So we really want to look at these two things together. P tells us whether or not the effects that we saw were significant. D tells us whether or not the magnitude of change was important or not. So for eligibility, eligibility is predefined to ensure that participants meet the criteria for the intervention. For example, they have a specific disease for a therapeutic trial, are free of disease for a preventative trial, etc. Usually eligibility is also defined by age, gender, race, state of health, etc. The narrower the eligibility criteria, the less generalizable will be the results, and participants must consent to screening for eligibility. Eligibility occurs after eligibility is established. Consent is provided after explanation of all study procedures, risks and benefits, measures to reduce risks, voluntary participation, compensation for injury, and compensation for time and effort. Randomization must be purely by chance. We can use random numbers, random computerized allocation, cannot randomize on any systematic characteristics, for example, digits of social security number, attendance at a clinic, etc. To maintain balance between arms, one can individually match by age, sex, etc., or block stratified randomization, randomize within blocks of 10 to 20. So what I did in a study that I did this past fall was I stratified based on schools. So I would individually randomize them per school. So at school 1, I would have 10 students, and I would randomize 5 to control and 5 to treatment. At school 2, I would have 10 students. I would randomize 5 and randomize 5. And then at school 3, I would randomize again. And then I will control for that when I do the statistical analyses later. Follow-up is conducted at predetermined intervals needed to detect the occurrence of trial endpoints. The frequency and duration of follow-up will depend on the type of endpoint, for example, response to treatment, development of new disease, progression of disease, or the level of risk. Higher the risk, more frequent the follow-up. So generally speaking, we're talking about the post-test in this case, and then we might do follow-ups to see if the effects that we saw at immediately after the intervention was delivered can stand up after 3 months or after 6 months. For attrition, losses are often selective. For example, high-risk persons drop out of trials, and this introduces bias. So if we were to look at the effects of substance abuse, a substance abuse program, the people that are not in the substance abuse program, that are in the control program, are going to be at a higher risk of dropping out of the study because we might not be able to find them at post-tests. Losses to follow-up should be comparable in the intervention and control arms to avoid biased comparisons, and losses to follow-up reduce study power by reducing the person time of observation. Blinding is done to minimize participant or observer bias. Double blinding, when neither the observer or participant know the arm of randomization. We have single blinding, where the observer, not the participant, knows the arm of randomization, for example, in cluster level trials. And unblinded, where we cannot conceal randomization, for example, in surgical interventions. For the analysis, we can do intent to treat, which means that we analyze all persons that were randomized, even if some do not receive the intervention or drop out before completion of treatment. This is least biased and most conservative. Or we can analyze the as treated people, and we are analyzing only those who actually complete the treatment. This is potentially biased by selection of the most compliant and often lowest risk population. For statistical methods, between groups on a continuous variable, we would use analyses of post-test scores. This is going to be the most oft used in our studies. And we would use a t-test, ANOVA, or ANCOVA. And we're looking at the post-test scores, but in an ANCOVA we could control for differences on the pre-test measure. We also have time to event, so time from enrollment until the outcome happens. In this, we would use Cox proportional hazard regression or hazard ratio or survival analysis. Outcomes at fixed points in time could be the proportion with outcome at each follow-up. This is logistic or binomial regression, odds ratio or prevalence rate, and intervention and control. So we're looking primarily in educational research at this. These generally have to do with more medical research. So this would be like post-test scores on a reading outcome measure, on a, what do we call it? So again, just to reiterate, between groups on continuous variable, this is the one that we are generally concerned with. Quasi-experimental designs that use control groups and a pretest. An example, a home health aid demonstration program provided selected welfare recipients with up to 6 weeks of training, followed by subsidized employment as home wakers and home health aides. To determine if this intervention improved earnings, researchers compared results from those who received training with 3 different non-randomized control groups. The control groups were those who applied for the program but left before screening, those who applied but were screened out by staff as ineligible, and those who applied and were accepted but did not participate in training. Comparison of results between treatment in all 3 groups suggested the training improved subsequent earning. The size of the effect depended on which control group was used. So it would look a little bit like this, where not randomized, not randomized. We give a pre-test, the treatment is delivered, and then we give a post-test. This is also called the non-equivalent comparison group design, perhaps the most common of all quasi-experiments. There's a pre-test and a post-test data on the same units. Threats to internal validity or external validity include, because the groups are non-equivalent by definition, selection bias is presumed to be present. This is where baseline equivalence comes into play. So if both groups were equivalent at baseline on measures that we found important, so on age, sex, socioeconomic status, and scores on the measure, we're at least a little bit better there. Also allows us to diagnose attrition and see if group allocation contributes to it. Threats can work together. For example, selection may work with maturation, where a select group may tire or improve at different levels. Selection instrumentation may occur when non-equivalent groups begin at different points on the pretest. For example, many scales have unequal intervals. For example, on a normed achievement test, getting a single item can have greater implications for percentile rankings at the extremes of distribution of the mean. Electronic GRE is designed to continuously get harder as you answer questions correctly. So, on a normed achievement test, getting a single item can have greater implications for percentile rankings at the extremes of a distribution of the mean. So if you scored a 63, you might not be near the cutoff of the percentile rankings, but if you hit a 64, you might be right on the line or have passed the line. So you could be in a completely different group, even though your change in the score was very small. Selection regression could occur, where individuals selected along a group line will regress to their respective means. Selection history, where an event affected one group more than the other, for example, many substitute teachers, etc. So if there was a lot of substitute teachers working at one school, and we did one school versus another school, we would see history being a threat to internal validity, because that school had a greater chance of not being taught by certified teachers. However, possible does not always equal plausible. Just because a threat could happen does not mean it is plausible that it did happen. For example, maturation is a threat for increased academic achievement, but it's not plausible for decreased academic achievement. Observed patterns of outcomes. Outcome 1. Both groups grow apart in the same direction. A common pattern of selection maturation occurs when initially non-equivalent groups grow apart at different average rates in the same direction. So, we have group 1 that's going up like this, and we have group 2 that's going like this. But they're both kind of going in the same direction. This one's still kind of going up. This one just happens to be going up further, which is what we hope to do. But we could also see something where group 1 starts way down here and goes up, and then group 2 starts here and goes up. If we just use the post-test score, this group was better at baseline, and they're also still better at so it's harder to note whether or not there was a treatment effect because we started at different points. For example, a study could examine the effects of frequent breaks on academic engagement in two schools. School number 1 receives breaks, school number 2 does not. In school number 1, academic engagement was initially higher and increased at a faster rate. School number 2, engagement was initially lower and increased slightly over time. Effects of this could have a lot to do with selection bias, and that school number 1 may have received the frequent breaks because they were already better students behaviorally, and the addition of frequent breaks compounded already good learners. The sort of selection could be seen in what was sold as an experiment in Tampa. Administrators, along with the university, set out to determine the effects of a single-gender schools on both behavior and academics. They then took two low-performing schools in the inner city and assigned one as the female school and one as the male school. The achievement of these students were compared to the other schools in the area. Major issues with this arose in the following. Schools were designated as magnets, and students had to apply to get in. School uniforms were implemented, and iPads had been provided on a 1-to-1 ratio. None of these things happened at any of the other schools, so it's hard to tell what made the impact of their behavior getting better and their academics getting better at these two magnet schools, because the schools that they were being compared to didn't have all of these other factors in there, and these factors would be considered confounds. What should be obvious is that any causal inferences from the schools being improved over surrounding schools are subject to serious bias on a number of levels. So back to the original example. Several methods can be used to detect selection maturation. If grouping differences are a result of selection maturation and differential growth between groups should also be occurring within groups, this could be detected through a one-way ANOVA. Higher performing students in this example would be maturing faster. The other outcome is that there's no change in the control group. In the previous example where we looked at frequent breaks, what if a teacher-student relations improved in the frequent break condition but did not change in the other condition? When controls don't change, it may be necessary to explain why growth did not occur when it did in the treatment group. Sometimes this would be obvious, but in things like reading, we would expect some growth to have occurred. So in a normal reading program, it may look like this, where it's going up ever so slightly. And then in our intervention, it may have went like this. So if this had gone like this, we would suspect that there was something very wrong with the reading program that was being done with these kids because they were actually getting worse instead of some growth occurring. Outcome 3, the initial pretest differences favoring the treatment group that diminish over time. The example they discuss in the book describes the study where they measured self-concept in African American children before and after integration. In their example, African American children who attended African American schools had higher self-concept while in their initial school, and it lowered after integration. Self-concept did not change in those already in integrated schools. So what we're looking at here is that you had these black students that were in a segregated school, and they had peer groups, and they had all of these things already intact. And then we moved them to an integrated school, and their peer groups would have gotten dissolved, and a lot of changes would have happened. There would have been likely bullying, there would have been all these things, so their self-concept might have gotten lower. However, if they were already in integrated schools, those things would have found their way out and worked themselves out over time. These kinds of threats are very rare but can happen. And then we have outcome 4, where the initial pretest difference is favoring the control group that diminished over time. In this case, the experimental group underperforms. This outcome is subject to typical threats of selection, instrumentation, and history. It's imperative to explore the reasons for group differences. So in this case, we had a control group starting up here that went like this. And then the treatment group started, let's say, a little bit higher, but only went to there. So we see that more growth happened here than happened here, and we need to understand why these things were taking place. Outcome 5, outcomes that cross over in the direction of relationships. In this type, control may stay even while group may have underperformed, or pretest and outperformed. Okay, in this type of outcome, the control may stay even, so we have the control going like this. And then we had the experimental group go like this. And so this is a really hard slide I need to go back there and re-look at this one. But essentially what we're saying is that the control group didn't make any changes, but we saw changes in the experimental group. But let's say the experimental group stopped here, we would still have post-test scores that remained the same. We would need to account for the fact that they started way down here and ended way up here. So we would need some way of statistically controlling for the fact that the baseline was not equivalent. However, any attempt to set up a design to achieve the outcome involves risk. One reason, power is low. It may look good plotted, more difficult to discern. While it may look good plotted, it is more difficult to discern significance. So one way to improve that is to have 2 pretests. So we have not randomized, or randomized in either case. So not randomized, this would be a quasi-experiment. We have 2 pretests. Give the intervention here, and then we give a post-test. This allows us to see if we had extreme scores on the pretest. These things will then even themselves out, and we would use some sort of an average, or when we're controlling for this, it would essentially give us an average score for the baseline and an average score here. Or we could switch replication, where we do a pre-test, we give the treatment to this group, and then we post-test both groups, and then we give the treatment to this group, and then we post-test both groups again, and hopefully at the end of this we will see scores that are similar for both of these groups. There might have been some, so we might have seen it go like this, and then they went up and stayed there, and then we might see it kind of tail off, because if this pre-test takes a long time to get there, they might not have maintained the results that they did over time as well. This design allows us to make causal inferences at two different points in time. Essentially, we demonstrate a functional relation. This design suggests that it's not absolutely necessary for the treatment to diminish in the first group to receive it as long as the second group shows the same improvement. This improves internal validity. Matching through cohort controls. A cohort is a success of groups that go through the same process. It's good for control groups if one cohort experiences a given treatment and earlier or later cohorts do not. So, for example, we look at freshman coursework over a period of time, and then we decide that we want to implement some sort of a freshman retention program. So we would look at the retention rates of, let's say, 5 years in the past where no course was added, and we can look at average retention rates, and then when this course is added, we can see if the intervention or if the retention rates improved, because we have 3 sort of controls, or 5 sort of controls, which were those earlier cohorts, and then we have a new one. And if we did this a number of times, we'd be able to come to some sort of conclusion. This is good for control groups if one cohort experiences a given treatment and earlier or later cohorts do not. If cohorts differ in only minor ways from their contiguous cohorts. Organizations insist that a treatment be given to everybody, thus negating other designs. An organization's archival records can be used for constructing and comparing cohorts. Assumptions. Selection differences are similar between cohorts that would be the case between non-cohort comparison groups. This is the case when we look at our blocks. Generally speaking, the people to enter the education program here are fairly homogeneous. The threats are history. This would be a big one, because it might be that at the same time we instituted this new program, we got a new football coach, so then everybody's school engagement improved or something. This is only useful if non-equivalent control group were added at exactly the same time points. Only if non-equivalent control groups were added at exactly the same time points can we address history. So the elements of design, which is not to be confused with ART's principles of design. We want random assignment if we can. We want some sort of cutoff-based assignment, which means that, like when we screen students in schools right now, there is a cutoff that would determine them to be at risk or not at risk, or some other non-random assignment. We might want to match or stratify, and we might want to mask. So masking would be good if we are doing observations on children, direct observations of children in a classroom. We would want to blind those observers so that we didn't know if they were in the control or the treatment group, because if we knew and we had some stake in the matter, like we designed the intervention or something like that, our observations might be tainted by the fact that we expect to see some improvement. Measurement. At post-test observations, we want a single post-test or a non-equivalent dependent variable, or we want multiple substantive post-tests. At the pretest observation, we'd like a single pretest, maybe a retrospective pretest, maybe a proxy pretest, which we don't necessarily want to get into. We might want to use repeated pretests, or we want to pretest and independent samples. We might also want to include moderating variables with predicted interactions. So if we were doing a study on fractions, we might want to see the moderating or mediating effects of their multiplication fluency up until that point. and we want to measure threats to validity. In comparison groups, we can use single non-equivalent groups, we can use multiple non-equivalent groups, we can use cohorts, we can use internal versus external controls, or we can use constructed contrasts where we extrapolate through regression. We use norm contrasts or secondary data contrasts. Generally speaking, we're going to be looking at these types of things. When it starts getting into these, things are going to start getting really complicated. In treatment, we can switch replications, we can reverse treatments, we can remove treatments, and we can repeat treatments. Is there an ideal quasi-experiment? Probably not. We can draw inferences from non-randomized studies, but it requires more data than randomized studies. Causal inference in non-randomized studies requires more assumptions and data analyses than in randomized studies, and we need to gather more data rather than making more assumptions. So now we're going to move on to regression. The assumptions, or the fine print in linear regression, we assume that continuous variables are used, either continuous or dichotomous, which means that we would have a 0 or a 1, or a 1 or a 2. The relationship between x and y is thought to be linear. We have a normal distribution in the scores. The variance of y at every value of x is the same, otherwise known as homogeneity of variances, and the observations are independent. And the reason that we're going over regression right now is because it has a lot to do with the assumptions of ANOVA. ANOVA is based on regression, and so we want to, I want to make sure that we're understanding the gist of regression as it relates here. And also when we get into regression discontinuity designs, we want to be able to understand the basic premise of regression so that when we plot out and look at that design, we look at that we understand the fundamentals behind it. So linear regression means that we are following a linear line up through, and so these scores, if this is the depression scores and this is hours of internet use, we can see that as their depression scores increase, as their time on the internet increases, the depression scores increase, and vice versa. The slope of 2 means that every 1 unit change in x yields a 2 unit change in y. So as we go over 1, we go up 2. And that's a slope of 2. Prediction. If you know something about x, this knowledge helps you predict something about y. So when we look at this, if we knew the value of x, we could predict what their score on y would be because our slope is 2. So if we knew that if x equaled 3, we would expect a score of 5 on the slope. When we do model summaries in regression, we're looking at this. We're looking at the R, which is the correlation between the two, 0.951. And then this is the percent change associated with a change in the independent variable. This is R squared, and it's 0.905. So this is the percent of change associated with the change in the independent variable. Then we have the ANOVA summary. And the ANOVA table reports how well the regression equation fits the data. So if it's significant, we're looking at that here, and that's under 0.05, so we would consider that to be a significant effect. And then we have the coefficients. So then these are also known as betas sometime, but we're going to call them coefficients for our purposes. So if y equals negative 5.68, which is here, plus 1.072, that is our regression equation. So we would be able to tell that y equals 50.4 because negative 56.85 plus 1.702 times 100 equals 50.4. And we see that these are both significant. So IQ was significant here at predicting something. Okay. So independence of observations, we use the Durbin-Watson between 1 and 3 equals OK. So our Durbin-Watson here is 1.854, and we would consider that to be OK in the independence of observations. When we're writing this up, a simple linear regression was calculated to predict test 2 score based on IQ. A significant regression equation was found, F, with degrees of freedom 1 and 103. So if we look back to this table, 1 and 103, and the F value is 974.306. We go back to the ANOVA table. We see that being right oh, there it is, 974.306. I don't know why it took me so long. Where P equals 0.00 with an R square of 0.904. In multiple regression, what if a disability or gender is a confounder here? We can adjust for gender and disability by putting them in the model. So if we have more than one predictor, each regression coefficient is the amount of change in the outcome variable that would be expected per 1 unit change of the predictor if all other variables in the model were held constant. The assumptions here, your dependent variable should be measured on a continuous scale. You have 2 or more independent variables which can either be continuous or dichotomous. We have independence of observations. We have a linear relationship. We need to show homoscedasticity. We need to not show multicollinearity. We need to have no significant outliers. And we need to have residual errors being approximately normally distributed. So then we look at the model summary here. We can look at the same kind of thing, but we use gender and disability as well as IQ. We see that it didn't affect this model too much. And then when we go to the analysis of variance, we see that the F score did slightly come down, but we're still significant. Our degrees of freedom also changed because of those other 2 predictors. So we have degrees of freedom of 3 instead of 1, and 101 instead of 103. And then for the coefficients, we have 1.069 for IQ, disability, and gender are both going in the opposite direction. So we can see a negative symbol here. And then we see the significance of these things over here, so neither of these significantly helped this model. So we could take them out and essentially get the same scores that we were getting before. To assess for multicollinearity, if we have these values going above 1 or 3, we see that they're no good, and we see that we have that here. Again, we have a strong one here between IQ and one of the predictors. We have another one here, we have another one here. These are all fairly big, so we probably have some collinearity there. So if we were to write this up, a multiple regression was run to predict test 2 scores from disability, IQ, and test 1. These variables statistically significantly predicted test 2 scores. F on 4 and 95 equals, this is degrees of freedom again, equals 32.393, P is less than 0.05, R squared equals 0.577. However, only one variable added statistically significantly to the prediction, P of 0.05, which was IQ. So again, this multiple regression didn't work as well as we would have wanted to. We controlled for these things, but we still got relatively the same results, and only IQ made a significant difference. So when we look at common multivariate regression models, we use linear regression if we have a continuous outcome variable. We use logistic regression if we have a binary or 2 zeros and ones on everything. And then we use time of event Cox regression model for time of event things. So if we're looking at the time it takes someone to drop out of school, if they have a specific disability or something like that, we would use Cox regression. But again, we're not focusing on these things. We're focusing on this thing. Now this is an important, these tables here are important to remember. It gives us an idea of the test that we would use depending on the data that we have. So if we have case control studies and we have categorical and continuous, we have two groups. On a continuous variable, we would use an ANOVA. If we have a continuous variable, continuous grouping on a continuous variable, we would use simple linear regression. If we have multivariate or categorical and continuous variables together on a continuous outcome variable, we would use multiple linear regression. If we have categorical variables here and a categorical variable here instead of a continuous test, so if we had grades instead of scores on a test, we would use the chi-square test or Fisher's exact test. So this is good. It tells us exactly what type of, so in a clinical trial, if we have categorical grouping and continuous variables, we could use repeated measures ANOVA, or we could use an ANCOVA. So again, if we have a continuous outcome variable and we have independent samples, we'd use a t-test, we could use ANOVA, linear correlation or linear regression, but generally speaking, we are going to go with a t-test or ANOVA, and almost always we will use this. If these things are correlated, we could use a paired t-test. So if if you were using scores from one group from pre-test to post-test, we would use a paired t-test, and then here's the assumptions that would go along with it. If we have a binary or categorical outcome variable, we would use McNemar's test, conditional logistic regression, or GEE modeling. And this is another way of looking at it. So we have a continuous variable, we have t-tests, we have ANOVA, blah, 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 blah. And again, binary or categorical outcome variable, we have chi-square tests, etc. And that is it for the group designs. The key points that I want you to keep in mind are, and we'll go over this more, the readings in the next chapter are going to be going over the What Works Clearinghouse standards for those designs. And so I want you to be clear on the difference between a randomized control trial and a quasi-experiment. And I want you to be looking at how you could, with your with the research question that you've already devised, I want you to start thinking about how you could turn that research question into either a randomized control trial or a quasi-experiment.